Good morning and good evening to everybody. We are very happy to welcome you for this seminar on the SLIA GRS structures. So my name is Antoine Dutin from the SLIA International Association. And on the behalf of the association, we are very happy. We thank you deeply for attending this seminar. So we have people attending from India, Indonesia, Philippines, and Japan. So before we start, let me kindly ask you to display as much as possible your affiliation and name on Zoom. So this will help us proceed with your question if you have any. Please mute the microphone and turn off the video. And for those who wish to apply for CPD, so this is for a civil engineer in Japan, please send us an email after the seminar. So you can leave any question or comments on the chat function of Zoom. And we'll have a question and discussion session at the end of this seminar, actually. So we will try to answer as much as possible all the questions that you may have, but we may have to select some of them due to the time limitation. So thank you in advance. So today's agenda is as follows. So first we'll have a brief opening address from Mr. Kosaka, which is the Chief Secretary of the SLIA International Association. So please, Mr. Kosaka, please proceed with your opening address.
Good day, everybody. Can you see it and hear me? I'm Takuya Kosaka, Chief Secretary at International Association of Serial Construction System, SRI. I'll deliver the opening address. Sorry. Thank you for attending today's seminar hosted by the International Association of Serial Construction System. About 120 applicants from 5 countries registered to attend this seminar. First of all, construction method is an abbreviation for reinforced soil railway structures with rigid facing, RRR, 3R. 3R construction method is widely used as earth reinforcement technology in common standard engineering practice, particularly for high-speed bulk train and conventional train lines construction in Japan. This slide shows the history of 3R structures in Japan as of April 2025. The total length reaches 221 kilometers. Remarkably, despite experiencing not only unexpected major earthquakes, but also various types of intensified seismic events without long and short period, the 3R structures have never suffered any damage. And then the 3R construction method has recently been adapted overseas as well. This table shows overseas project for 3R structures in operation. Among these cases, Tomita will introduce an example of Indonesia Jakarta MRT depot later. This table shows overseas project for 3R structures under construction. We are pleased that many members of L&T and TCAP attend today's seminar. This table shows overseas project for 3R structures currently under planning. Yeah, I will explain the background of establishment of our association. Now, overseas projects for serial construction method are on the rise, but most of them are ODA, Official Development Assistance Projects. So, design consultant in Japan involved in the design. A general contractor in Japan is in charge of the construction, and geotextile material from Japan is used. Now, high quality for serial construction method shall be ensured in overseas projects. So there shall be no problem with the safety performance of the structures constructed following the serial construction method. However, from now on, an overseas company is in charge of the design and construction of serial construction method, and if the geotextile material is also locally produced. Urgent issue is how to ensure the quality, safety, and performance of such serial structures constructed overseas. So, to develop a serial construction method in overseas projects, we established RRI Association in 2022. Okay, part of the activities of 3RI Association, the technical seminar on serial construction method will be held. This is today's seminar program. Professor Emeritus Fumio Tatsuoka from University of Tokyo and Tokyo University of Science Japan will give a lecture titled Geosynthetic Reinforced Soil Structures Developments from Walls to Bridges. And Dr. Yuichi TOMITA from Tokyu Construction Co. Limited will give a lecture titled Typical Construction Case Histories of Serial GRS Structures. The program is scheduled to end at 4:30 p.m. So it will be a bit of a long term, but I hope today's seminar will be interesting and fruitful for all of you. This is that. I'll turn to my opening address. That's it.
So we'll move on with the lecture from Professor Tatsuoka, but before this, I would like to introduce Professor Tatsuoka. Oh, you know, yeah, not So he is a Professor Emeritus of the University of Tokyo and the Tokyo University of Science in Japan. So he was the Vice President of the ISSNG, which is the International Society for Soil Mechanics and Geotechnical Engineering, President of the Japanese Geotechnical Society, Vice President of the Japanese Society of Civil Engineers, and President of the International Geotechnical Society. So he specialized in the deformation and strength characteristics of geomaterials, ground improvement, including cement mixing and soil compaction, as well as, of course, geosynthetic reinforced structure. So he started quantitative research on this topic since 1982, so almost 40 years ago. Quite some time. So I will, without waiting, leave the floor to speak to Professor Tatsuoka. So please, Professor Tatsuoka. Yeah.
Pointer. Okay. Good morning or good afternoon. I'm Tatsuoka. The topic today is the synthetic reinforced soil structures, developments from walls to bridges. So, abstract. これ邪魔だな。Okay. The developments of the various types of the synthetic reinforced soil DRS structures with full height rigid FHR facing, including those for high-speed railways for the last about 45 years, will be reported. The total wall length has exceeded 221 kilometers as of April 2025. Fine. これあ、こっちこれIn the 1980s, GRS retaining walls was developed. With this GRS structure, after the deformation of the backfill and subsoil by the construction of reinforced backfill has taken place, the full height rigid facing is constructed by casting in place fresh concrete directly on the grid wrapped wall face. In the early 1990s, GRS bridge abutment was developed. With this GR structure, the full height rigid facing supports one end of a simple girder via a bearing. In total, about 200 have been constructed. In the early 2000s, GR's integral bridge was developed. Both ends of continuous girder are integrated to the top ends of full height rigid facing of a pair of GR retaining walls. 14 have been constructed. A number of conventional type embankments, retaining walls, and bridges that collapsed by severe earthquakes, floods, ocean storm waves, tsunami, etc., were restored to 3RGR structures with full height rigid facing. So the performance of all these 3RGR structures during and after construction is satisfactory, while very high cost effectiveness has been validated. The contents. The first is the recent GR structures for high-speed railways in Japan. This is showing the network of high-speed railways in Japanese Shinkansen. This white and black stripes are the lines in service, and this red part is under construction. So this part opened March 2016. This one site, Mantaro site. Here is R is the GR's retaining wall. A here and here is a GR's bridge abutment. GR's internal bridges, I is not here, and B is GR's box culvert, and T here is a GR tunnel entrance exit protection. All these GR structures were constructed in place of conventional type structures. This is a cross view of this site. This is GR's retaining wall. This is GR's box culvert. Here is the GR's tunnel entrance exit protection, and this is the GR's bridge abutment. So GR's bridge abutment is constructed in this way. First is shallow ground improvement when necessary, then construction of GR's wall. At this stage, no facing. So this is the view at this of the structure at this stage. Then third, full height rigid facing is constructed, and the bearing a simple girder, then completed. This is a view after the completion. So this side Kyushu here. This line opened to September 2022. Here is a GRS retaining wall at the Omar Depot. Highest wall is 12.4 meter. In this route of high-speed railway, in total, 88 bridge abutments were constructed at the tunnel exit, right here and here and here. Among 88 bridge abutments, 78, that is 89%, are 3RGRS bridge abutments. This is a GRS bridge abutments, and here is a RC viaduct between tunnels. Here, this is one site, and GRS bridge abutment on this site, and the other one is the other site. This is a small, narrow valley. Here is a GRS bridge abutment. And this is short viaduct. And this is the other GRS bridge abutment. This is another site. This is now train is now coming. This is bridge abutment. This is the construction procedure of GRS integral bridge at Genshu. First is the excavation of subsoil, then the construction of approach field. This part is a zero grit reinforced, well-compacted, lightly cement mixed gravel soil. And then the construction of full hydrate facing after the deformation of the backfill and subsoil has taken place sufficiently. Then the arrangement of PC girders. Here's one shot showing this placement of PC girder. Then the structural integration of both ends of the girders to the full hydrate facing, then construction of slab and others to complete the bridge. Yeah, this is GRS bridge. But in integral bridge, this is GRS wing retaining wall. This is the view of this site. Here is a GRS integral bridge, and this is GRS wing road. This is continuous RC slab track, no ballast. And this is showing the structure of GRS tunnel entrance exit protection. So this is showing the arrangement of the grid layer and compaction. Yeah. So second is showing the construction of GRS walls on both sides of tunnel. Then finally, this showing construction of full hydrate face RC facing here. This is not structurally connected or connected to the RC lining, RC tunnel lining, to avoid any interaction between two parts of the structure. And here is a Oshamambe site under construction. This is a picture I took this last May, and this is a GRS integral bridge. And soft subsoil was improved. And this is a view of GRS retaining wall. This is a GRS bridge abutment, an abutment of GRS integral bridge. I visited this site only 1 week ago, and it was snowing very cold. This is the PC girder. Span is 30 meters. This was produced at the site. And this is showing the history of 3RGR structures until April 2005. This is annual wall length. And this red one is a total. So now the total length exceeded 221 kilometers. And during this period, this is the restart of construction of new high-speed railways. After this, many high-speed railways were constructed. And during this period, we had a number of serious earthquakes like this, and no damage to these structures. So the construction started in 1989. Research started before that. This is showing the location of completed 3RGR retaining walls, bridge abutments, integral bridges, etc. And this number is a project sites. And this red one is the GRS bridge abutment or GRS internal bridges. So far, project site is 1,466, and including 4 overseas sites. So far, no problematic case during and after construction in all these projects. This is an important point of this technology. Summary of the first part. A number of the synthetic reinforced GR structure with full height rigid facing have been constructed in place of conventional type retaining walls, bridge abutments, and simple girder bridges. In Japan, these GR structures have become the standard railway structures. The GR structure were constructed also for roads. Besides, they were constructed at several overseas sites in Vietnam, Indonesia, Philippines, and India. This success can be attributed to the fact that, compared with conventional type soil structures, these 3RGR structures exhibit, first, higher performance against long-term static and traffic loads, and severe earthquakes, heavy and prolonged rainfalls, strong floods, ocean storm waves, and tsunami, and the lower cost for construction and long-term maintenance. The next topic is extensive versus extensive reinforcement and flexible and stiff facing. This is a theoretical and technical background of this technology. We have various types of mechanically stabilized earth retaining wall because we have a flexible versus stiff facing and inextensible and extensible reinforcement. Facing flexible means we have no high earth pressure does not develop on the facing. So this is the definition. Stiff facing develops high earth pressures on the facing. The other factor is inextensible reinforcement or extensive reinforcement. Inextensive one, typical one is a metallic strip, and extensive one is a typical one is a polymer planar grid. This one is facing the metallic skin facing, tailor-made. The B is a discrete panel facing. This is also tailor-made. C is a wrap-around facing with a grid reinforcement. And this D is a modular block facing and grid reinforcement. ポイントは見えてないの？sorry。ポイントは見えてないの？これはこれ。見えてる？ OK。OK。sorry for interruption. And yeah, the modular block facing with the grid D. The last one is E. This is a stiff facing, fluid rigid facing with a the grid reinforcement. This is 3RDR written wall. So previously, many considered that for small wall deformation and high wall stability, it is necessary to use inextensible reinforcement such as metallic strips. This one. However, this notion is not realistic. That is, although the grid is relatively extensible, the grid reinforcement is planar with a high throughout strength, and the grid is stiff enough to effectively reinforce the backfill when arranged at a small vertical spacing. For 3RDR structure, this is 30 centimeter, and the grid is free from corrosion. Previously, many considered that facing is necessary only to prevent spilling out of backfill, and the earth pressure on the facing should be kept low for small deformation and for small wall deformation and high wall stability. So flexible facing A or C is sufficient. However, we often observe that when using flexible facing A or C, the earth pressure is low, whereas the wall deformation is large, sometimes too large. So this is indicating that indicating the paramount importance of using stiff facing to develop high earth pressure. This one. So when the facing is flexible, we have a very low earth pressure on the facing, which results into low tensile forces in the reinforcement, in particular at low level of the wall. And in the active zone, we have a low earth confined pressure, therefore low strength and stiffness of the backfill. So we have a large wall deformation and low stability of the wall. On the other hand, we consistently observe that when the facing is stiff and firmly connected to the facing reinforcement layers, that is B or D and E, the large earth pressure develops, which results in small wall deformation and high wall stability. So when the stiff facing is firmly connected to the reinforcement, we have a high earth pressure on the facing, which results in the high tensile forces in the reinforcement, in particular, even at the low level of the wall. Then in the active zone, we have a high confined pressure, therefore high strength and stiffness of the backfill. Then so we have a small wall deformation and high stability of the wall. This is the basic concept of 3RDR written wall. So the use of discrete panel here, discrete panel facing or modular block facing, this decreases the wall deformation and increases the wall stability. However, the use of fluid rigid facing is much more effective for small wall deformation and high wall stability, and much more advantageous in many other aspects. This is I'm going to explain. So the next topic is the multiple functions of full height digital facing. First of all, conventional type retaining wall is cantilever structure. With this structure, we have a large forces in the facing. This requires a massive and strong facing structure. Besides, we have a large overturning moment and large lateral thrust load at the facing base. This results in a large stress concentration at the facing base and unstable behavior, particularly by severe seismic loads. So we usually use a pile foundation. This is a collapse of gravity type wall, one type of cantilever wall during 1995 Kobe earthquake. So we can see the overturning failure. So on the other hand, full height digital facing for GR's retaining wall is a continuous beam supported by many reinforcement layers. So at the small span, 30 centimeter, this mechanism of facing is utterly different from one of the cantilever structures. So we can expect several important advantages. First is a very small forces in the facing, and so simple structure is sufficient. Second is a small overturning moment.
Apa ini?
A small
Okay.
lateral thrust load at the facing base. So a pile foundation becomes unnecessary and the wall becomes stable even against severe seismic loads. So this is a picture of GRT wall with full height facing at Tanata. I took this picture in 1992. I took this picture 1995, a week after 1995 Kobe earthquake. You can see a collapse of the Japanese house. The wall survived. Yet we had a noticeable shear deformation about 2.7%, and second, lateral displacements at the base about 2%. This slightly exceeded allowable limit of deformation. Why? This is because this wall deformation was not excessive but noticeable, which was due to that all the grid layers were short, only 2 meters. That is 0.4 times the wall height. So H equals about 5 meters. This design was adopted as the use of longer grid layers that interact with existing railway tracks on this wall was not allowed. This grid arrangement was exceptional. Yet we confirm that safety factor is larger than allowable minimum 1.5. This was satisfied in the seismic design using a horizontal coefficient of seismic load 0.2, following the design code that was effective at the time of design of this wall. So we did some investigation of this earthquake. One of that investigations was shaking table test, simulating the retaining wall during this earthquake. This is a gravity wall that collapsed. This is a DRT wall. The grid layers are all short. We observe some displacement, but not collapse. So the shaken table tests on these and other world models were performed to confirm the high seismic stability of GR13 wall with full height facing, and to find the necessary and sufficient grid length to ensure high stability against high seismic loads. So this is the results. So these seismic loads were applied, increasing the amplitude step by step, like this. This is the displacement at the top of the facing. This is the displacement of gravity type. Collapse at this acceleration, seismic coefficient about 0.6 to 0.8. This is a displacement of DR retaining wall, R1 type. All the grid layers are short, so more stable, yet the displacement is not small. So we examine the stability of the other type or other types of conventional type cantilever wall, this type or this type, all show the similar trends of behavior, all large displacement showing a brittle behavior. On the other hand, we examine the stability of three types of the grid arrangement. R1, this is the actual one at the site. R2, only two layers of the grid were extended to extended long. R3, all the grid layer is 0.7 of the wall height. So we can see that the R1, R2 is more stable, R3 is also more stable than R1. So R2, this one, is more stable than R1 and similar as R3, whereas more cost-effective than R3 because of the less amount of the grid used and less amount of the excavation when constructed on slope. So now R2 is a standard type of current arrangement of the grid in the current design. So this point I will explain more in detail. This is typical arrangement of grid layers in R2 type. So here's a short basic grid layers. In addition to these short basic layers at a vertical spacing of 0.3 meter, long grid layers extended to the plane of reports, that this angle is 35 degrees, are arranged at the vertical spacing of 1.5 meter. So why we need this short grid layers here, I'll explain to next. Gentle slopes are often reconstructed to vertical walls, particularly in urban areas. However, the two reconstruction methods shown below, this one method, are costly and needs a long construction period due to large slope excavation we need and the use of temporary support, such as anchored sheet pile. In the case of zero-grid wall, if this is a modular block facing, then we need a long zero-grid to ensure the stable behavior wall. So we need the large excavation, and we need a sheet pile and anchor. So these two cases, so conventional cantilever and MS retaining wall having a discrete panel or modular blocks and using a relatively long grid, we need a large amount of excavation and expensive temporary construction system. Then we propose DR retaining wall with full height facing. This is a solution. Here's a short basic zero grid. Then we can reduce slope excavation and no use of anchored sheet pile. And this is a typical case in Tokyo. So you can see the short basic reinforcement layers. So excavation is largely reduced. Yet the track is located very close to wall face and no pile foundations. So the reduction in the wall stability by the use of short basic zero-grid layers is covered by the use of first, densely arranged planar zero-grid layers having a high pull-out strength. So vertical spacing is 0.3 meter. The second is the use of several long zero-grid layers here, and the use of full height ridge facing. This is designed to be strong and stable enough against earth pressure and external loads. So, the use of densely grid layers and several long grid layers here, and the use of full height facing, these enhance monolithic behavior of the enlarged reinforced zone without developing a local internal failure. So then we can expect a substantial increase in the wall stability against overturning, lateral sliding, and shear deformation. These are caused by back pressure, particularly seismic earth pressure, and external loads at near and full height facing. So then advantageous feature this high stability in spite of low construction maintenance cost of full height lit facing is taken advantage. Then we developed GR's bridge abutment, GR's internal bridge. This is the next topic. Before that, so this is the stability analysis of GR's retaining wall having full height facing. First is internal stability, and this external stability. The length of short basic grid is determined by the internal stability analysis, this one. So then we determine this length. So this is some details. So anyway, the length of the basic grid layers is largest value among 35% of the wall height, 1.5 meter, and the length required to keep the wall deformation lower than allowable value against level 2 design size load. This deformation is by overturning or lateral sliding and shear deformation. These are by two-wedge analysis for internal stability. But details are here. So then we perform as a part of internal stability analysis. The full height lead facing is designed to be strong and stable enough against the internal forces in the facing structure that are developed by earth pressure and external loads. Then we examine external stability. Some details are described here. Please read if you are interested in. So then, multifunctional full height facing, in summary, the facing is important and essential structure or component to confine the backfill by developing large tensile forces in the reinforcement and to support other structures. So during service, facing should be stiff enough. So I'll skip this part. So during construction of the reinforcement, the temporary facing should be stable enough and deformable enough to accommodate deformation of the backfill. So this is a contradiction. So completely one is stiff, but during construction, facing should be flexible. So this contradiction can be solved by stage construction. This step, I'll explain this procedure next. Advantages of construction of full height rigid facing after the construction of reinforced backfill. So this is like this. This is before the start of the reconstruction of the slope. Then this is a completed backfill, but this is before the construction of full height rigid facing. This is a completed wall. Now full height rigid facing has been constructed. This is a detail of this construction. First is the leveling part and the embedded part of full height rigid facing is constructed. Then placing a temporary facing. This is welded steel wire mesh in this case. Then the first layer of soil is placed and compaction like this, and this is repeated to complete the wall. The good compaction of the backfill is achieved by first a small lift, 15 centimeter, ensured by a small vertical spacing, 30 centimeter, between the grid layers, and no rigid facing is existing during backfill compaction. Then this is completed wall, but before the construction of floor-height rigid facing. Then after the sufficient deformation or sufficient compression of the backfill and subsoil has taken place, floor-height rigid facing is constructed by casting in place fresh concrete directly on the grid wrapped around wall face. Here is the external concrete form, but no internal concrete form. Fresh concrete is cast in place. Then the fresh concrete enters the crushed ground zone held in the temporary facing unit. This case, the welded steel wire mesh through the aperture of the grid layer, the grid. Then the floor-height rigid facing and the grid layers are firmly connected to each other. This is a shot showing the field test to examine the connection strength between the facing and the temporary facing. In this case, it's a gravel field bags, no separation by this lift upping of the test piece. We also performed the laboratory separation test. We confirmed that the separation strength always much higher than necessary separation load. Separation load. In this case, this is equivalent to the inertia of 0.5 thick facing by horizontal acceleration, 1g. This is required, but the actual separation strength is much higher. So the property required for the grid are first, sufficient tensile strength and stiffness with low creep deformation. And the second is a high anchorage strength in concrete and backfill. Third is a good adhesiveness with concrete. Fourth, this is important, high long-term durability against high pH of concrete. Term 2, 3, 4 are important for 3RGR structure system. The grid is in direct contact with fresh concrete, like this. So this is a typical one by axial PVA grid, satisfying all these requirements, 1, 2, 3, 4. So now wall is completed, this typical one. I took this picture 15 years after the completion, 2006. Still, of course, this is surviving, of course. So this next is advantages of stage construction, this step. First is very small different settlements between floor-height rigid facing and the backfill during and after the wall construction. And the second is temporary facing units consisting of welded steel wire mesh and crusher line protects the facing and the grid connection. So essentially no damage to the facing the grid connection during long-term service. For example, even when subject to severe seismic loads. And the construction of GR's retain wall using a compressive backfill and/or on a compressive subsoil becomes possible. One typical case here, very difficult construction conditions because soft soil layer 30 meter and base and the soft soil was used soft backfill was used as a backfill. If we use a conventional retaining wall, we need a long piles. Actual structure like this. These difficult problems were solved by stage construction. First is the GR wall without facing and preload fill. The settlement is about 1 meter, then removal of the preload fill. The final construction of floor height rigid facing. This is a view of preloading stage. So 1 meter settlement, then preload was removed, floor height rigid facing. I took this picture 20 years after the construction. So required performance of facing for DR structure is first. During construction of the grid reinforced soil without floor height facing, this stage, temporary facing should be not only stable enough to keep the temporary wall stable, but also deformable enough to accommodate the deformation of the backfill and subsoil by the construction of the grid reinforcement wall. This stage. And against static and traffic loads and severe seismic loads and other natural disasters during long-time service, floor height rigid facing should be stiff and strong enough to keep the the wall deformation and ensuring high wall stability. So these contradicting requirements can be satisfied by the stage construction in which floor height rigid facing is constructed after the deformation of backfill and subsoil has completed. Next up is GR's bridge abutments and GR's internal bridges. So this is showing a number of serious problems with conventional simple girder bridge. First, we construct piles. Next is our abutment. Then we backfill. Then problem starts as pressure and displacement, and settlement and lateral flow of the subsoil. Then we need many long, strong piles. In addition, here the bearing. Bearing is costly for construction and long-term maintenance. And we have a long-term settlement here. And by the seismic loads, we may have a large settlement and this damage to bearing and dislodging of simple girder is possible. So what is the solution? One solution, so this is the next topic. This is the conventional simple girders. Many problems. One solution is this GR structure. The other one is structure, internal bridge. So this GR structure, I explain, first generation and second generation. This is the first generation we developed. First, we constructed GR's retaining wall, and then this girder foundation, small girder foundation. This is not integrated to floor height rigid facing. Then we arrange movable or fixed girder bearings. Then we place girders. So we have no bump right back of the floor height facing. So we have a low maintenance cost. A stable approach field. This is very stable. High cost effectiveness. However, we have two remaining problems with the long, heavy girders. One problem is large seismic inertial load acting to girder foundation where fixed bearing is arranged, and girder ends supported by movable bearing become unstable. This is an important issue in seismic countries, high seismicity countries. Second is the settlement of the girder foundation due to the compression of the underlying backfill. This may become unacceptable. So now we developed the second generation. Here is a GRS return wall. The girder foundation is stabilized by integrating to full height ridge facing, then bearing and girder. So now we solved two problems. This is much more cost effective. So this is a typical case. First stage of the bench cutting of the slope and construction of the GRS bridge abutment and the construction of the full height rigid facing. And this is a completed one, bridge abutment here. So GRS bridge abutment, two apartments in this case, then we can construct a simple supported bridge like this. This is a typical case. Both are GRS bridge apartment. This is also possible. So summary of the GRS bridge apartment. First GRS bridge apartment was 2023 at Tanata, and the 2012, the highest one, was constructed. As of 2025, in total, about 200 have been constructed, many for high-speed railways in Japan. So GRS bridge abutment of this size is very advantageous. However, we have two unsolved problems. One is a high cost and for construction and maintenance for bearing, and the second is low seismic stability of the girder at the bearing. So now we developed GRS internal bridges to alleviate the two problems. The bearing is a problem. So now combining two technology, one is GRS bridge abutment, second is internal bridge. So we have a GRS internal bridge. This is constructed in this way, ground improvement if necessary, GRS wall, full height ridge facing, and girder is placed. Then finally, the structure integration. So this is static, then we perform static and dynamic tests to evaluate the performance of GRS internal bridge. This is a small model test, static cyclic lateral loading test. We apply a small cyclic displacement, simulating the thermal expansion and contraction of the bridge. So this is a air dry sand. By applying this small displacement D, like this, only 6.6% of the wall height, then the earth pressure is increasing to a very high value, and the settlement is very large. So earth pressure increases and settlement is large. Why such a thing happens? This is due to dual ratchet mechanism. This continuously developing both backfill settlement and earth pressure. Suppose we have this active displacement, then we here the formation of active wedge, a settlement. Then we apply the passive movement here. The active zone, active wedge deforms and displace as a part of the passive wedge, not recovering the settlement that took place during active one, no back. And we have a development of passive wedge, so increasing the facing pressure. So then this is the second active displacement. Then the deactivation of the active wedge and settlement, and no development of passive wedge. Then second passive, then active wedge does not never recover its displacement, but the activation of passive wedge developing additional earth pressure. So when we apply a cyclic displacement here, the settlement is like this when the displacement amplitude is 0.6% over the wall height, and point to person like this. When we arrange the grid, but no connection, there are no connection between facing and the grid. Settlement still large. When the grid is connected to facing, now no settlement. And we performed a shaking table test. This is the model and of the GR internal bridge. Central mass is to simulate long girder. So we apply a shaking at the base of the facing. This is the typical results. The displacement at the top, d sub t, displacement d sub b. This is dt. 4 models. And this is the base acceleration. Conventional types show a large displacement at the top and also bottom. This GR's bridge abutment first generation. Here the dislodging displacement of the and this bridge support. So this is the right displacement. And the integral bridge shows the right displacement at the bottom. And the GR's integral bridge shows the largest resistance. This acceleration exceed 800. So the strength can be increased by increasing connection force. And settlement here, conventional type show large settlement, and integral bridge shows large settlement, and integral bridge show nearly no settlement. Based on a number of many researches, we constructed a full-scale model of internal bridge about 15-meter height and 5-meter height, 15-meter long and 5-meter high. So we performed the lateral cyclone test, simulating seismic loads and thermal effects. So we confirmed the very high stability of this type of retaining wall and type of bridge. So we constructed a number of GR's internal bridge. I show here the 3 GR's internal bridge constructed here. This is a collapse of conventional simple girder bridge. 2 simple girders had been washed away towards inland by great tsunami from the Pacific Ocean. So there are 3 proposals for restoration. One is a previous one, old one, 2 spans and simple girder. The second one is a single continuous girder, but still we use a movable bearing. The third one is a GR's internal bridges. No bearing, everything is integrated, and the backfill is reinforced with the grid. So we evaluated the construction cost, seismic stability, anti-tsunami stability, and need for maintenance. In all these design conditions and for these design conditions, GR's integral is the best. So we decided to construct GR's integral bridge. This is the bridge at Koikorobe. The total span length is 40 meters, and this is shot during construction. This is the completed one. So another one is here, Haipe. So here, 2 simple girder has washed away by tsunami from the ocean. And this is now 60 meters in span. Central pier is supporting the vertical load, but everything is integrated. This is a bridge GRS bridge abutment before the construction of flow height facing. This is a complete one. So the arrangement of this is showing the arrangement of the the grid for GR retain wall. In this case, the grid longer at the top. And this is the arrangement of the grid for GR bridge abutment, longer one at the bottom. This is opposite. The reason is this: for GR retain wall, this should be short, and train or road is running in the direction perpendicular to this figure. So small difference in the settlement and stiffness between unreinforced zone and reinforced zone is not a problem. On the other hand, GR bridge abutment, now very large girder load by inertial load of the girder is acting to this top of the reinforced zone, passive and active. So this should be very stable against overturning. So the gravity of the reinforced zone should be low. So this is more stable than reversed one. And also trains running in this direction in parallel to this figure that is in perpendicular to this full hydraulic facing. So this thickness of backfill should increase from 0 to larger one continuously to avoid any discontinuous settlement, to avoid the bump. But actual one is a different shape under different site conditions. In any case, bump is avoided, and also stability is ensured by stability analysis. So summary, GR's bridge abutment is typically support one end of simple girder on a fixed bearing arranged at the crest of full hydraulic facing, this one. The second one is GR's integral bridge. Structure integrates both ends of a continuous girder to the crest of the full height facing of a pair of GR's retain walls without using any bearing. So compared with the conventional bridge structures, these GR's bridge structures are much more cost-effective, exhibiting no bump right behind the facing. So while much more stable against severe seismic moves, strong floods, and tsunami. There are now standard bridge structures for railways, including high-speed railways, Shinkansen. They are also applicable to road bridges in the same way as railway bridges. Last topic is the restoration of soil structures that collapsed by earthquakes, floods, ocean storm waves, and tsunami to GR structures, some other cases. This is the case during 1995 Kobe earthquake. Here the collapse of the cantilever retain wall during 1990 Kobe earthquake, and this is a restoration to GR's retain wall or someplace nailed wall. Another case is a failure during 2004 Niigata Kenchibu earthquake. We had a number of failure of the road and the railway embankment like this. This is a structure on slope. So this blue one is a structure before the collapse. Here's a gravity retain wall, slope, and railway. This was reconstructed to this red one, GRS retain wall. This is the first train. This is during reconstruction. And the height is about 13 meters. So this is another site. You can see collapse of the embankment. The railway track is slid down. This is the complete one. So we for conventional type cantilever retain wall, one of the typical failure is by scarring in subsoil. Then we have an overturning failure. Then we quickly have a collapse of embankment. Then the function as a road or railway is lost. GRS retaining wall with full height facing fifth in different way, even we will have scarring, the overall failure does not take place. So function as a road and railway can be maintained for emergency. 207, we have a large-scale collapse of the seawall by ocean stone wave. This is a collapse of the ocean collapse of retain wall, seawall, for a length of 1.5 kilometer, and this will we have a scarring here. This is Pacific Ocean. Then this is restored to GR's retain wall, like this. This is a view during construction. This is Pacific Ocean. This part is under before construction of flow height facing. This is a casting place of concrete concrete or flow height facing. This is complete one. I took this picture 201, 2010, and I took this picture 2023. So on average, 2 times per year, ocean storm waves taken in beach sand gravel particles attack the wall, overtopping the wall. This is another case of collapse of wing wall for a bridge abutment. And here is a collapse of a masonry retain wall. This is a close view. This was restored to a GR's abutment and retain wall like this. Only 10 days required. And construction of flow height facing was after opening of service. More large-scale failures here during 2013 flood. Here's the collapse of the railway embankment. Here's the railway. Height is 30 meters. Here's the river is running here. Then here's the river is running, attacking the wall embankment. This is after restoration, but before the construction of flow height facing. So this is a cross section of this embankment, this railway, and this is after the flow height facing was constructed. This has been very effective to prevent the failure of the wall by scarring by this river flow. So, concluding remarks. First, number of GRS retain walls with a full height facing, GRS bridge abutments, GRS integral bridge, etc., have been constructed as an important permanent structure for a total wall length more than 221 kilometers as of April 2025. This is not a temporary structure or important permanent structure. Many of them for high-speed railways, Shinkansen, and also part of them are roads. This success is due to first, high performance during long-term service and against severe earthquakes, heavy rainfalls, strong floods, and tsunami, etc., and low cost. This is important. Low cost for construction and low cost for long-term maintenance. In particular, low cost for long-term maintenance is very important. The zero-grid GRS bridge abutment, typically supporting one end of simple girder on a fixed bearing here, arranged at the crest of flow height facing of a GRS retain wall. So this is much more cost-effective and much more stable than conventional type bridge abutment. In total, about 200 have been constructed. All of them are performing satisfactorily with essentially zero bump here, 0 bump. All of them are performing a 0 bump, yes. This is now one of the standard bridge abutment structures for railways in Japan. GR's integral bridge consists of a continuous girder with both ends being structurally integrated to the crest of the full-height ridge facings of a pair of GR's retaining walls, not using girder bearings. This is much more cost-effective and much more stable than conventional simple girder bridges. In total, 18 have been constructed. Many are now under design. GR's internal bridge is now one of the standard bridge structures for railways in Japan. Many of the conventional type embankments, retaining wall, and bridges that collapsed by recent severe earthquakes, heavy rainfalls, strong floods, storm ocean waves, tsunami, etc., were restored to GR structures having a full-height bridge facing. This is a really typical case. The following are 3 breakthroughs necessary. It was necessary to develop these GR structures. First is the use of full-height ridge facing for changed from low earth pressure to high earth pressure on the facing. This is the first essential point. Second, from a secondary non-structural component to a primary structural component. Second breakthrough is a stage construction for changes in construction sequences from facing before backfill to facing after backfill. That is, facing is constructed after the construction of backfill. So third is structural integration of first full-height facing to reinforce backfill, and also the girder to full-height ridge facing for GR's internal bridge. This is for changes from statically determinate but unstable structures to a statically indeterminate but stable one. So thank you very much for your kind attention. Okay.
Thank you, sir.
Okay. Okay. So sorry for this.
Okay, so thank you, Professor Tatsuoka. So we'll move on to the second lecture, which is given by Dr. Tomita. So just before this, let me remind you that you can leave any question or comments in the chat. We'll have a discussion session at the end of the seminar, and the question in the chat will be given priority. But so before let me introduce Dr. Tomita. Okay, so Dr. Tomita is now the principal researcher in the Technical Research Institute of the Tokyo Construction Corporation in Japan. He's also a part-time lecturer at the Nagaoka University of Technology. So he obtained his PhD from the University of Tokyo in Japan. He's also a professional engineer and a PEC engineer. He also actually graduated from Tokyo University of Science from the laboratory of Professor Tatsuoka. So he joined Tokyo Construction in 2006, worked on reinforced structure, and also was the design manager for the Jakarta MRT project, on which he will talk, I think, in this lecture. And he's currently involved in research and development on geotechnical engineering. So I will leave now the floor to Dr. Tomita. So Dr. Tomita, please proceed.
Thank you for kind introduction. Good afternoon. I'm Yuichi Tomita from Tokyu Construction. Now I'm going to make a presentation about typical construction case histories of 3RGRS structures. So I have three typical construction case histories of 3RGRS structures. First one, track expansion for a major Shibuya-Yokohama commuter line using the 3R method. This project focuses on the track expansion work in the Hiyoshi area here, located between Shibuya and Yokohama. This section is one of the busiest commuter routes in Japan, so increasing rail capacity was an important goal. Today, I will explain how the track was expanded in this area and now how the 3RGRS structure was applied in the project. This slide shows the typical cross-section in the Hiyoshi area, where the plan was to expand the line from the 2-track to 4. The left figure shows the original 7-meter embankment with masonry retaining walls and 2 tracks on top. The right photo shows the site at the beginning of the improvement work. The left side figures show the 4 steps of track switching sequence by widening the crest of the embankment. Original, improvement work, track switching, and then completed. The 2 existing tracks were shifted onto the newly widened area. Finally, 2 additional tracks were constructed to complete the expansion project. The right figure shows the improved embankment structure, consisting of 3R nail and 3RGRS. 3R nail was used to reinforce the lower embankment with large diameter soil nails. 3RGRS was applied above it to build geogrid reinforced soil retaining walls. The 3RGRS uses a reinforced concrete wall facing called full-height rigid facing, together with geogrid reinforcement to confine the backfill effectively. In the 3R nail, we use large diameter nails instead of small diameter nails. This reinforces existing embankment that is cut to a nearly vertical wall. In this project, we applied the so-called radish anchor system. Each anchor is about 40 centimeters in diameter, which gives high pull-out resistance, allowing the use to short nails and efficient construction. Construction process. The construction was carried out in the following several main steps. First, cement mixed soil column wall was constructed by in-place cement mixing to remain the nailed soil wall during cutting. The existing masonry retaining walls were cut step by step, stabilizing the embankment by installing radish. After the nailed walls were completed, the geogrid reinforced backfill was constructed by the 3RGRS. Finally, an RC full-height rigid facing was cast in place to tie the nail reinforced slope and the geogrid reinforced backfill together. A strong connection between the RC facing, the nail heads, and the geogrid layer is essential. This is showing the construction of cement mixed soil column as the temporary retaining wall for nail reinforced wall. Here is service line. This is showing the installation of a radish anchor into the embankment cut to a vertical wall. This process is made after the soil in front of the cement mixed column wall was excavated to the required depth. Then the soil was mixed with the cement milk from a soil cement column inclined from the horizontal. Then tensile core rod was placed at the center of the cement mixed soil column to produce the large diameter nail radish anchor. This is showing the arrangement of geogrid reinforcement. In this process, the backfill material is spread and compacted after each geogrid layer is arranged over the compacted backfill. This cycle, spreading and compaction of the backfill and geotextile placement, is repeated layer by layer until the embankment reaches the designed height. Then, to complete the structure, the reinforced concrete full-height rigid facing was constructed. Finally, the reinforced concrete wall, called the full-height rigid facing, was constructed on the front of the reinforced soil structure. This facing completes the 3RGRS system, providing a rigid surface and protecting the reinforced soil behind it. With the compression of the full-height rigid facing, the entire structure was finished. This is showing the completed wall on the opposite side. This is the end of the case history of the Hiyoshi 3R project. Second is first implementation of the 3R method in Indonesia, perimeter retaining walls for the Jakarta MRT depot. The aim of this MRT network is to connect the north-south and east-west the capital city of Indonesia, Jakarta. Our company was responsible for the south end sections CP101 and CP102 of phase 1. The 3R method was applied at the vehicle depot located at the south end here. This slide shows the outline of the project. CP101 includes the depot, viaduct, and station works. In terms of quantities, the depot covers an area of about 83,000 square meters. And the total embankment volume is roughly 300,000 cubic meters. This is showing the perspective drawing of depot. The depot extends about 700 meters east-west and 200 meters north-south. Around the perimeter, retaining walls with heights from 1 to 5 meters were constructed. These walls from the boundary between the depot, the national road, and city road. The 3RGRS retaining wall was adopted as the outer retaining wall, shown by a thick red line in this figure here. It was constructed over a 510-meter section, about 30% of the total perimeter, where the wall height exceeds 2 meters and the structure is close to the track. In the original basic design, as shown in this figure, the outer retaining wall was planned to be a reinforced soil wall composed of precast concrete panels and geogrids, which are discrete panels commonly used in Indonesia. For this wall, pile foundations were necessary. However, by reviewing the basic design, we found the following several problems. First, railway tracks of the depot and the storage lines are located very close to the wall face. However, the facing consists of discrete panels, which doesn't ensure sufficient stability of the backfill close to the wall face. Second, after the contract award, the client required an additional design check about seismic stability. However, it is difficult to ensure sufficient seismic stability with this wall using discrete panel facing. Third, the client required a fence top of the wall, but with a discrete panel facing, the geogrid and the fence foundation interfere, so fence cannot be supported stably. In addition, the client asked us to omit the pile foundations under the wall to further shorten the construction period and reduce cost. However, this request was a major technical challenge because in several areas at the retaining wall site, the subsoil had an N value less than 6, very soft ground conditions. For these reasons, we decided to revise the basic design. We adopted the 3RGRS retaining wall, as all these problems cited above can be solved. This slide shows the 3RGRS retaining wall adopted for the project in Japan. This sorry. This slide shows the 3RGRS retaining wall adopted for the project in Jakarta. In Japan, this method is widely used for railway embankment because it is cost-effective and provides excellent seismic and long-term performance. It also allows fence foundations to be placed the full height rigid facing and enables the omission of pile foundations. For these reasons, the 3RGRS structure was selected. In this system, geotextile layers are placed every 30 centimeters and firmly connected to the full height rigid concrete facing. The typical reinforcement length about 40% or more of the wall height, and every 1.5 meters are longer layer added, extending to the 30-degree line from the base. The 3RGRS structure consists of geogrid reinforcement, crushed stone, backfill soil, anchors for the facing formwork. These elements are placed layer by layer from the bottom. After confirming the ground has stabilized, the RC full height rigid facing is cast to complete the wall. This slide shows how the 3RGRS system addresses the key challenges of this project. First, challenge 1. The tracks were located very close to the wall face. 3RGRS has been widely applied to railway embankments in Japan, and its stability in narrow space is well proven. For challenge 2, seismic design was required. The system has excellent seismic performance with strong track record, making it suitable for earthquake-prone areas. Challenge 3, installation of fence and utility poles. The RC full height rigid facing allows these foundations to be directly connected to the wall, which meets the project requirements. Finally, challenge 4, omission of piles. With 3RGRS, the reinforced soil structure is built first, and once ground stability is confirmed, the RC full height rigid facing is constructed. This approach solves the construction difficulties on soft ground without using piles. Based on these advantages, the 3RGRS structure was considered an effective solution for all major challenges of the project. For the 3RGRS retaining wall, Japanese engineers provided technical guidance and on-site training to the local staff. This helped ensure that proper construction procedures were followed and the required quality was maintained. Geogrid reinforcement is installed at the heights, orientations, and lengths specified in the design. Standard length layers are placed every 30 centimeters of compacted backfill, and longer layers are added every 1.5 meters of height. The backfill surface is carefully leveled to avoid any unevenness, so that horizontal tensile forces are distributed evenly across the geogrid. A temporary facing unit is placed to hold the backfill in place until the RC full height rigid facing is cast. Welded wire mesh and anti-spill sheet are set, followed by spreading crushed stone and backfill soil. These are compacted together, and after compaction, the geogrid is folded back over the compacted surface from the wall side. After confirming the quality of the backfill material, it is spread to the required thickness and compacted with a vibratory roller. Near the walls, smaller compaction equipment is used to avoid deforming the temporary facing. Care is taken to prevent the compaction equipment from directly contacting the geogrid or facing materials. Because the concrete facing uses no rear formwork, steel anchors made from a lever welded to equal angled steel plate are installed inside the backfill. The angle steel is fully embedded to avoid damaging the geotextile above and to ensure no steel protrudes from the fill surface. The steps described earlier are repeated until the reinforced soil embankment reaches its planned height. Once completed, settlement at the top surface is measured to confirm that no further residual deformation or defects remain. Finally, the reinforced concrete full-height rigid facing is constructed by casting the concrete in place at the wall front, completing the 3RGRS structure. In this project, the fence foundation anchors were installed at the top of the full-height rigid facing, integrating the fence foundation with the 3RGRS retaining wall as required by the client. In addition, the RC full-height rigid facing was also used as the foundation for electric poles. In many previous 3RGRS retaining wall projects, the RC full-height rigid facing has been used to support various structural components, not only fences and utility poles, but even bridge girders. Therefore, the client requirements for this project were fully met by applying the 3RGRS structures. This project was successfully completed and opened to operation on March 24, 2019. This photo shows an overall view of the finished depot, where the completed 3RGRS retaining wall may be seen here. Third, GRS integral bridges for the Sanrik Railway reconstruction project. The Sanrik Railway Lias line is about 163 kilometers long. Many sections run close to the coastline. In 2011, the Great East Japan earthquake caused a huge tsunami. The tsunami severely damaged tracks and stations of the Sanrik Railway at many locations, and the entire line was shut down. This presentation shows the construction of the GRS integrated bridge used for the restoration between Omoto and Tanohata stations here. These pictures show typical damage caused by tsunami along the Sanrik Railway Lias line. The upper left photo shows Shimanokoshi Station before the disaster, located right beside the coastline. In the bottom left, the Shimanokoshi Viaduct after the tsunami. Its girders were completely washed away, leaving only the piers. In the upper right photo, the Koikorobesawa Bridge was heavily damaged by the strong tsunami flow. And finally, in the lower right, the Haipesawa Bridge, the girders were displaced and the abutment was destroyed. These photos clearly show the severe impact of the tsunami on the railway structures. This is the GRS integrated bridge constructed in the Shimanokoshi area. It is the two-span continuous reinforced concrete slab bridge with a central pier built with the river channel. The bridge dimensions are 27.4 meters in length, 8.4 meters in height, and 20 meters in width. On top of the bridge, a reinforced embankment is constructed, forming a stable and continuous soil structure. This slide shows the construction sequence. First, ground improvement was carried out, followed by the installation of the cast-in-place concrete piles for the central pier of the GRS integral bridge. Next, the front portion of the GRS abutment approach blocks on both sides were constructed. After that, the full-height rigid facing and the central pier were built, and temporary supports were installed to hold the girders during construction. Then the GRS abutments were completed, and the continuous girder was constructed. Finally, the GRS soil layer over the GRS integral bridge was placed up to the design height, completing the entire structure. The upper photo shows the site prepared for the bridge reconstruction. Ground improvement was then carried out using sand compaction piles to stabilize the subsoil layers. Next, the river was diverted and the riverbed subsoil was excavated down to the formation level for the bridge. Construction of approach block and central pier here. The front portions of the approach blocks, the full height rigid facing, and the central pier were constructed. After that, temporary supports for the bridge girder were installed. Construction of the approach blocks continued, and the formwork for the girder slab was placed. The GRS approach fields were also built up, and the slab concrete was cast. Finally, the GRS embankments on both sides and the reinforced soil layer above the bridge were completed. With this, the bridge construction was finished, and the temporary supports were removed. The approach block provides a smooth and stable transition between the neighboring embankment and the bridge. It is constructed by compacting cement-treated crushed stone reinforced with geogrid reinforcement layers. Cement and crushed stone were mixed in a tank using a backhoe. This procedure is to produce uniform cement-treated gravel for the approach block. The geogrid reinforcement layers were placed every 30 centimeters. Long geogrid reinforcement layers were placed at every third layer. The design tensile strength 30 kN per meter with the short standard geogrid and 60 kN with the long geogrid here. The photo on the right shows the construction process. Placing the geotextile, spreading the cement-treated backfill material, and compacting it with a 1-ton vibratory roller. These steps are repeated layer by layer. A train is now operating over the completed GRS integrated bridge. The Sanrik Railway Kitarias lines resumed the service on April 6, 2014, marking the full restoration of the entire railway line. Today, I presented 3 case histories of 3RGRS structures. Each project has different goals and different site conditions. Even so, all of them used the advantages of the 3RGRS structures to solve their engineering challenges. These examples show the high flexibility and strong performance of the 3RGRS structures in many types of railway structures. We will continue to promote this technology to help build safer and more resilient railway infrastructure. Thank you very much for your kind attention.